Excellent. Well, I think we're ready to start now. We have 50 participants logged on, which is a great number. So I'm Dr. Christina Vanderwell. I'm from the University of Southampton, and I'm here chairing the session for the Breathing City Future Urban Ventilation Network seminar series. So just a little bit of background about the network that I'm sure you all know, but our aim is to bring together researchers and people from industry and to take a health evidence approach to urban building design. And so our seminar series are meant to explore this topic with leading people from the field. So just a bit of housekeeping for today. What we'll do is we'll please keep all the questions until the end of the talk, and we'll enter the questions in the chat channel, please, and I'll be able to read them and collate them and then let the speaker address them at the end. Please, everybody, keep yourself on mute while we're listening to the talk, and we're going to respect each other's contributions during this talk. Today's event is being recorded, and we also have an active Twitter account at Breathing City. So if you're using Twitter and would like to tweet about this talk, please do, and please tag us. So just an overview of all the people involved in the Future Urban Ventilation Network. I'm in the top left corner there, but there's a large committee of people involved in this network that are steering it, and lots more people involved in the events that we hold. And finally, here's also a list of a lot of the industry that are participating. So hopefully we have a good representation here listening to this talk. And what I'll do now is I'll stop sharing my screen. And if Nick, do you want to get your slides ready while I introduce you, please?
Yep.
Excellent. So today we have Professor Nicola Carslaw, who's a professor of indoor air chemistry from the University of York, and she specializes in numerical modeling of indoor air pollution chemistry. She's notably the associate editor of the Journal of Atmospheric Environment, and has also been recently working as an advisor on the SAGE environmental modeling group in relation to COVID. So I'm very excited to hear about what she has to say today. Nick, I'll pass it to you now.
Okay, thank you very much, Christina, and thank you very much for the invite to come and talk to you all today. So I'm aiming to talk for about maybe 30 to 40 minutes, so we can leave some time for discussion at the end. I'm just going to admit this person into the talk so that goes away. So just an overview here about how the talk will be split up. So first of all, I'll talk a little bit about why we should study indoor air pollution, and I'm sure to most of the audience here that's fairly clear. And then to think about why there's a focus now, thinking about sources of indoor air pollution and implications of those sources. And then finally, at the end, just talking a little bit about some solutions as well. So this is a slide I always put up for my students, and it's just to get them thinking about the context for indoor air pollution. And what I tell them is that those numbers at the top there are all in years. And so what I do then is ask for volunteers. Now I'm not going to be able to see the chat, so we're going to have to break all of the rules. And I'm just going to ask someone to shout out if they know what 79 years might represent.
Lifespan.
Exactly that. So in the US, average male life expectancy 79 years. So obviously that's going to be pretty much the same for females or for other developed countries. So given that, and given the title of this talk, big hint here, where do you think you may spend 70 of those 79 years?
Indoors.
Exactly. So if you think about all the regulation around air pollution, it all focuses on outdoors. So if you drive around any major city in the UK, you will see outdoor air quality monitors, and they are looking at the concentrations in the outdoor air, making sure that they stay below regulatory standards. So despite the fact that we spend 70 out of 79 of our years indoors, about 90% of our time, all the regulation focuses on outdoors. So we can break that down a little bit more and think about particular microenvironments. So what about 50 years as a particular microenvironment where we spend 50 of our 79 years?
At home?
At home, yep, that's right. And then what about 26 years?
At work?
No, might feel like it sometimes. That's about a third of your life.
In bed.
Asleep.
In bed, yes, asleep. So I always say though that if you have teenagers like I do, these two may well be reversed. But in theory, about a third of your life spent in the bedroom. And then we have to get all the way down here to 5 years before we get to the average proportion of your life that you spend outdoors. So again, just to reiterate, this is where all the regulation is around these 5 years out of your 79 that you spend outdoors. And yet there's currently no regulation. And then this one right here at the end is commuting. Okay, so that's the context. We obviously spend a lot of our time indoors. And then if we look at a bit more detail at some other issues, why study indoor air pollution now? So lots of things have changed over the last 30, 40, 50 years. So it's a bit cliched, I guess, but if you look back 1950s, 1960s, kids tended to be sent out of the house in the morning to go and, you know, make themselves scarce and come back for the tea. So there's lots of outdoor play. Nowadays, there's a lot more time spent indoors. Children like to do Xboxes. And again, I know this from my own experience. They spend time on their phones. You know, there's a lot less going outdoors to play than there used to be. And this is also reflected in the adult population, where we've gone from maybe jobs that involved being outdoors, farming, towards more office type jobs. So there's been a shift in our behaviour to spending more time indoors. On top of that, if you look at things like the tightness of houses, so the ventilation rate in your average house, what we're looking at on this plot here is the year of construction of different buildings against the mean air change rate. So don't worry about the units. What's important here is the trend. And you can see that over this period from about 1940 going through to more or less the present time, houses and buildings in general have become more airtight. And then the final plot here is showing consumer index. And the reason this is important is because we buy lots of new things. And we know that new things, very broadly, if we think about things like furniture, give off higher emissions when they're new. So you can see that these three things have combined to give a kind of perfect storm. So we're spending more and more time indoors, in buildings that are becoming more airtight, and we're bringing more things into those buildings that give off emissions of things like volatile organic compounds. And then if you kind of put that into the context of COVID as well, the last year and a half or so, we've been spending even more time in our homes. So all of these things mean that studying indoor air quality at the moment is extremely topical and extremely important. And if you think about your typical home, there are lots of sources of indoor air pollution. Some of them are summarized here, so some are quite obvious. So if you're in a kitchen, you might be cleaning, same in a bathroom. You could be cooking and generating some pollutants, but some are less obvious. So, you know, things like maybe fiberglass, maybe pets, obviously allergies, everyone knows about things like these, dust mites, but also things like printers and photocopiers in some homes. So there's some really obvious sources, some less obvious sources. But again, this needs to be considered in the context of that building over time becoming more and more insulated and less well ventilated in general. So let's think now for the next little while about some of the sources of pollution indoors that lead to particularly high concentrations. And these are some of the sources that we think about at York in my group. What we're really interested in is looking at the direct emissions, but also thinking about how those direct emissions can lead to some chemistry indoors. So I'm not going to talk too much about chemistry today because I know that not everybody in the audience is an expert in chemistry, but we will talk about some of these high emission activities and what the implications are. So things like cooking, cleaning, scented candle use and air freshener use are all sources of indoor air pollution that can lead to quite high concentrations. So this image here is just to remind me to mention smoking. So if you smoke, or if you live with someone who smokes, that's going to be by far and away the biggest source of exposure to air pollution that you're going to receive in a building. But there's lots known about that, and I'm not going to talk about it today. I'm going to focus more on these sorts of sources. So because of all those sources indoors, what might surprise some of you is that when you start to look at the concentrations of volatile organic compounds, and again, this is something that we study a lot in my group, we're interested in how these species degrade indoors once they're emitted. And the concentrations of many of these species are actually much higher indoors than outdoors. So formaldehyde is an obvious one here. So you can see the concentration indoors is typically much higher than outdoors, getting on for a factor of 10. And the reason for that is that it's in lots of wooden products, things like preservatives on wooden floors, for instance. It can also be formed through the chemistry indoors. So many of these species that we think about as indoor pollutants can actually be much higher concentrations indoors. So let's home in on a few of these sources now. So cooking is quite an interesting one. So we know that cooking can generate particles, and that's what this figure is showing here. It's showing you the number of particles per cm cubed of air from cooking different types of food. And you can see that these have all got slightly different emission patterns, so slightly different sizes. So this is showing you the size of the particles along the bottom. So some foods produce smaller particles when they're cooked, some produce bigger, some produce higher concentrations. And you can see that this highest peak here is caused by cooking sausages. This is followed by bacon, and then cheese, and finally some sort of vegetables at the bottom. These are aubergines. And there is a general trend from experiments that have been done around cooking indoors that shows that cooking meat tends to give off higher concentrations of particulate matter than cooking vegetables, which, if like me, you're a vegetarian, is very good news. So that's one thing to think about. These plots here come from an experiment called Home Chem that was held in America in the summer of 2018 in Austin in a test house, and they did lots of cooking experiments, lots of cleaning experiments. And what they found was some quite interesting results. So this time what we're looking at is PM concentration. So this is the weight of particulate mass per meter cubed of air. And these different colours represent different size particles. So the orange is the really fine particles, and then we're going up to bigger particles as we get to the pinks at the top of these bars. And what they did over this, the course of these experiments, was to cook different types of meals. So the first bar here is breakfast. And interestingly, even though this is an American experiment, this was an English fry-up breakfast. So bacon, sausages, mushrooms, and you can see that we're generating quite high concentrations of particles. So again, to put this into some sort of context, these concentrations are probably 10 to 20 times higher than you would get outdoors under typical conditions. You can see that toast produced some particles as well, though not as much, perhaps not surprisingly. And then we've got a big peak here from cooking a stir fry. And again, that's because this involves frying meat at high temperatures. That's where a lot of those particles are coming from. So chili is not quite as big, or lasagna, and that's because there's probably less frying in the preparation of these two. Once you add the tomatoes, the particle emissions slow down quite considerably. So a lot of variation depending on the food type. And then the Americans in this study also tried to simulate typical Thanksgiving Day, where they cooked, the whole shebang with turkey, cranberry sauce, and everything else. And this is, again, looking at different sizes of particles. So smallest are typically at the bottom, these traces going up to the biggest particles at the top. And you can see different activities during the day lead to different, to higher or low concentrations. So for instance, here's breakfast being prepared, and you can see a peak of particles associated with preparation of breakfast. Then this little peak here is caused by some toast. And then they start to do some activities. So they start to prepare the stuffing, and then they start to prepare some pumpkin pies. And then there's a bit of a decrease in particles until they start to prepare the turkey and put it in the oven. Here's where somebody burnt an oven mitt. And then we've got a peak here for preparing the Brussels sprouts. And the reason for that is that they tend to stir fry Brussels sprouts rather than steam them or boil them like we might do in the UK. Then the guests arrive, the ovens are turned off, and you can see the particles start to come down again until someone blows out a candle. So these pollutant traces provide a really nice kind of trace of the human activities indoors. And this study generated quite a lot of media interest around, you know, what there were some quotes about cooking was worse than walking down a road in Beijing and this sort of stuff. So it did get quite a lot of media attention. Okay, and the reason we worry about health effects of producing that really fine particulate matter is the health effects, and the really fine particles can get all the way down into the alveoli, enter the bloodstream, and then potentially cause damage. Okay, so that's cooking, and the other compounds that we're interested in indoors, apart from the particulate matter, are the VOCs, the volatile organic compounds, and their degradation products indoors. And we're quite interested at York and elsewhere in studying these fragrance chemicals that end up in a lot of the personal care products we use indoors. So things like limonene, which is a citrusy smell, linalool, which is the smell in lavender, one of the predominant smells, and also pinene, which you get from pine trees. So these things are all natural products, but they end up put into a lot of personal care products that we use, so they're synthetically produced as well. And the thing about limonene and the terpenes is that their chemistry is very complicated. So I did say at the start I wasn't going to show you much chemistry, but I am showing this one slide. And what this is basically trying to show you in a nutshell is the oxidation steps from the parent hydrocarbon. So right in the middle here, we've got limonene, and that is shown in red as the parent hydrocarbon. And then every time the color changes, we're getting one step away from that parent hydrocarbon. So what it's showing you is that all these different colors mean another level of degradation of the compound. And you can see that there's probably 9 or 10 steps. And every time we have another step, we get lots more compounds. So we start off with limonene, but to fully understand its degradation indoors or indeed outdoors, we probably have to consider about 500 species and 2,000 to 3,000 reactions. So it's very complex, the chemistry as well. And maybe this is a simpler way of understanding the chemistry. So this picture was taken in a gentleman's bathroom in the US, not by me, I hasten to add, in case you're all wondering. And what we've got going on here is a kind of air cleaning device that emits ozone. And we've also got a kind of air freshener. So not a good idea to have these two things together. You can see quite clearly at the exit from the ozonizer that you've got some sort of reaction happening here. It's already starting to discolor. So this is seeing chemistry in action. Okay, so moving on to think about scented product use. We love using scented products in the UK. So these are some sales figures. It's actually really hard to get hold of anything more up to date, but you have to pay lots of money to get hold of the sales figures generally. And these are showing for 2016 and 2017, the kind of units of scented product that people buy. So this is things like air fresheners, scented candles, smelly fabric fresheners. So going from right to left on a particular year, we're going from the people who don't use many of these products every year to the people who use lots of these products. And bearing in mind, these are in thousands, so this is 3.5 million units. So there's 3.5 million people who use 13 or more of these units of scented products per year. So there's a massive, massive market for these things, and particularly with scented candles. So the markets for scented candles are increasing very rapidly. So there's a value here for the US that in 2016, there's about $7.5 billion spent on these things, and it's expected to increase to about 11.7 by 2025. So enormous growth. And you will all have seen the Yankee candle shops where you can get every scent under the sun, including usually, very ironically, fresh air, which always makes me laugh. But some countries are really, really into scented candles. So the Danish absolutely love scented candles and burn more kilos of candles per head of population than any other country on the planet. And it's all wrapped up around this kind of hygge lifestyle where, you know, everything's better with a lighted candle in the background. Now, there was an interesting study that came out of Denmark, and it basically looked at 56 Danish homes, so not a huge sample size, admittedly, but nevertheless, what they did was they looked at the integrated exposure in these 56 homes to particulate matter, and then they looked at the sources of PM in the 56 homes. And the interesting thing was that by far the biggest single component of their exposure coming from burning these scented candles. So that's where any of these bars are coloured in purple. That is the part of their exposure that's due to scented candles. So you note that all of the really high exposures are from the homes that burn lots of scented candles, and even in the ones that are lower in terms of their totals, quite often the scented candle is a big portion. So these things are being used, particularly in some countries, and obviously people are being exposed to quite high concentrations of particulate matter as a result. But there are lots of other fragrance products that you can buy. You can get diffusers, you can get these plug-in air fresheners, and these also give quite high concentrations of fragrance compounds when they're used. So this plot on the left here is showing you one of these diffusers, and you can see that the concentrations, these are in micrograms per meter cubed of the fragrance substances, and these are shown with these little solid symbols here, can reach several hundred micrograms per meter cubed. So these are quite high concentrations. The interesting thing in this experiment as well is that they added some ozone in here just to see what would happen with the chemistry. And you can see that when they did that, they immediately made a very large peak of particles, and they're shown, oh no, they are on the same scale, sorry. And the same here, this is now an electronic air freshener, and these are now showing the number of particles on the left-hand scale and the concentration of the fragrance compounds on the right-hand scale. So note that some of the compounds of the concentrations of the fragrance compounds are higher with the electronic air freshener. That's because these things are heated up to about 60 degrees or so, I think, so that you are liberating more of the fragrance into the atmosphere than the kind of static diffusion things that just sit at room temperature. So you can get even higher concentrations of some of these fragrance compounds. And again, during this experiment, they added some ozone and proved that you could make a very big particle peak as well. So basically, if you're using these things, particularly on a summer's afternoon where there might be high ozone concentrations outdoors, that ozone can come in through the windows and react with any of these things that you may be using in your home. Okay, so cleaning products have also been in the news recently, and there was a study that came out in Science in March 2018, which was really interesting for the whole indoors versus outdoors relative importance story. And I guess up till this point, you know, we'd always been thinking about indoors, how it was influenced by outdoors. So if you live near a busy road, you'd keep your windows shut because you were worrying about stuff coming in. And this paper was the first one that really started to think about, well, hang on a minute, what about what we use indoors? And, you know, that going back out again, how is that important? And I guess before this, there was a thought that wasn't really that important, that all we had to worry about was outdoor air pollution. Now, what this study showed was that we have lots of volatile chemical products that we use in our homes. So I've shown you some of the sources already. But the way that this paper turned all of our thinking on its head about it was that this showed that products that we use indoors, these VOCs we're using indoors, were probably responsible for nearly half of the VOCs that we're measuring outdoors. So that was a really important finding. And the other thing to remember that I'll come back to at the end is that this is only going to get more important over time, because we're thinking about, you know, vehicles are becoming cleaner, technology is improving, we're electrifying the fleet. So as outdoor emissions of VOCs go down, these indoor sources are going to become even more important for outdoors as well as indoors. And here's a real extreme of that kind of indoor cleaning scenario. And this is extreme cleaning, and it goes on in some places, probably in the US, some hospitals use this. It's also used in some laboratories to clean them up, and some food manufacture places, not in the UK as far as I'm aware. And basically what they do is they use these no-touch devices, so you can see it in this picture here, and they wheel them along into a setting, maybe a hospital ward, and then I should say, by the way, they do take the patients out first, but then they turn these things on and they generate massive concentrations of disinfectant gases. So formaldehyde, 1000 ppm, 25 ppm of ozone, 500 ppm of hydrogen peroxide, or chlorine dioxide up to about 350 parts per million. So they would turn these on, seal up the room, leave it for a couple of hours to generate these very high concentrations, ventilate the room, and then start using it again. So we looked at this, and we looked at it in terms of the chemistry that followed and different lighting conditions. So what we did was we simulated one of these events with the model that we use at York, and we basically assumed that the ventilation was stopped, the emission of this no-touch device started, we let it emit for an hour, we then let it sit there for another hour before we turned the ventilation back on. And what we were interested in looking at was different lighting conditions, but also just seeing what some of the radical concentrations were like when you put these massive concentrations of disinfectants into a room. So basically the only safety requirement is that the disinfectant gas has to come back down to a certain level before you can use that room again, but nobody's really looked at the, you know, the ongoing chemistry. So that was what we were interested in exploring. And what this is showing, don't worry too much about the detail, but this species in the middle, the hydroxyl radical, is a very strong oxidant. And what we could see was that under some lighting conditions, and this is the one in particular, this is when you had a bare fluorescent lamp, which you might have in a hospital ward perhaps, you could get extremely high levels of this oxidant. And you can see here, these levels are about 1 to this, probably more than that, sorry, maybe 5 to the 7. And this is probably a factor of 10 higher than this oxidant reaches outdoors in the presence of sunlight. So the reason that's important is because once the hydroxyl radical is indoors at these levels, it can react with things like volatile organics and produce that particulate matter that's harmful to health. So this was really interesting to look at in terms of the chemistry going on, but also has led to recommendations that if you're going to carry out this sort of cleaning, you carry it out in the dark, which is what's happening over here when you have much lower concentrations of radicals that can be produced. Okay, so just checking time. So one of the other things we're working at York is to try and start to think about an indoor emissions inventory. So outdoors, these have been done for many years. We've got the National Atmospheric Emissions Inventory. So we have a pretty good handle on the quantities of VOCs that are being emitted outdoors. But at the moment, there's nothing like that for the indoor environment. So along with some of my colleagues in the chemistry department, so Ali Lewis's group, we've been looking at how you can start to think about a sort of bottoms up approach to an indoor emissions inventory. And this is some really neat work carried out by Amber Yeoman. And what she did was she looked at 7 or 8 different types of shampoo and shower gels, moisturizers, foundations, conditioners. And for each of those, through a series of careful experiments using gas chromatography, mass spectrometry, she was able to identify the concentrations and hence emission rates of different volatile organics. So they're all listed here at the bottom in these different products. So these are just, you know, market leading products that we bought from a supermarket and then just carried out these tests. So you can see that there's variation between the different types of shampoos and then also between the different types of products. Now, once you have those sorts of emissions data, what you can then do is put that into a model and start to understand the implications of their use. So what we did is some model simulations, and we basically assumed we had an ensuite bathroom, about 5.5 cubic meters. We also assumed that this bathroom was using a fan during showering, so at about 9 air changes per hour. So this is quite high, but also to say that very few people actually use fans when they shower. It's not automatic by any means. And then what we wanted to do was set up a typical kind of shower scenario. So it's actually, you can actually Google online, how long does the average shower take? And I was quite surprised that a shower could be this long, without you all thinking that I don't spend long enough in the shower. I suppose I was thinking, does it really take whatever we've got here 2, 4, 7 minutes to have a shower? It certainly doesn't take me that long. But then again, with reference to the teenagers in the house, maybe that's not so unrealistic. So we're assuming that someone's taking 2 minutes to apply shampoo, 2 minutes to apply conditioner, 3 minutes to use their shower gel. They then spend 3 minutes drying and 2 minutes applying moisturizer afterwards. And when you do that under these conditions, you can see that we can get quite high concentrations. So 70 parts per billion of ethanol, over 300 parts per billion of limonene, 80 parts per billion of methanol. So these are high concentrations, and certainly not concentrations you would see outdoors unless it was very extreme conditions. You can also see there's quite a long tail. So this is, 7:30 in the morning. And then you can see that some of these species actually hang around for quite a while, even after the shower has ended. And then this is just, a part of the story. So what we're also doing through another project that's running at York, an EPSRC funded project, is looking at cooking and cleaning. So different types of meals, different types of cleaning activities, and can we start to build up this kind of emissions inventory for indoors that can allow us to look at how people behave, and then to predict what their indoor exposure might be, because buildings are so different and behavior is so different. So maybe if we can build up some sort of emissions inventory on a behavioral basis like this, we can start to understand what the indoor environment might be like. Okay, so this is sort of a little bit of chemistry, but not in detail. Now, one of the interesting things about your skin is that it contains things like squalene. And squalene is a very big volatile organic compound that contains lots of carbon-carbon double bonds. And we know that carbon double bonds like to react with ozone. So if you are in a room and there's any ozone in it, this reaction will be happening on your skin, and you will be producing these sorts of emissions. And we know this because people have measured in rooms where there are lots of people, and they can measure all of these compounds building up. And this is a CFD simulation. I thought I should put at least one CFD simulation in for this audience. And what this is showing is ozone at the top and a skin oxidation product at the bottom. And just to show you what that looks like, so the concentrations are going from blue to red, low to high. And here we've got an air inlet with air from outdoors coming in. That's relatively high in ozone. And we know that ozone tends to stick to things when it comes indoors, including people. So you can see that there's low concentrations around the simulated person here, and that's because their skin is removing that oxidation product. And then you can see the opposite sort of pattern with the oxidation product. So we've got low concentrations of that coming in from outdoors. There's none of this outdoors basically, but you can see that as the ozone passes over the person, you can start to build up this product. And then because of the ventilation pattern, you end up with a high concentration of this oxidation product in the corner. The other thing that's going on indoors is breath emissions. And when everybody knows that you breathe out carbon dioxide, but probably people don't understand as much that you breathe out lots and lots of different compounds. And this is a gas chromatography. I haven't been drinking, honestly. A gas chromatography analysis of breath. And every one of these peaks is basically a different hydrocarbon, okay? So breath is very complicated. It depends on your age, your gender. It depends on what you've been eating, whether you smoke. So, no two people look alike. Now, the thing about breath and skin emissions is that they can behave very differently indoors. And this is why it's quite complicated sometimes thinking about solutions for indoor air quality, and because you don't want concentrations to build up. If you're looking at things like breath emissions, so isoprene is in breath. Now, if you increase the air exchange rate for isoprene, you will just dilute the concentrations because it's coming from an indoor source, and the more air you add in from outdoors, obviously the lower the concentration will be, you dilute it. However, with this skin oxidation product, you see a very different pattern, and this is really interesting. So obviously, as you dilute the room, add more air in, you would dilute the product that's formed, but you're also bringing in higher ozone concentrations from outdoors, which help to make that product. So you can see this is fairly flat for quite a portion of these ventilation rates, until at some point the dilution will become more important. There's only so much ozone you can bring in, even if you open all the windows wide open. So your kind of mitigation strategy needs to take into account all these different complexities. Right, I think I'm just keeping an eye on the time. Just a couple more things to go through now. So these are some really neat experiments from Germany that I thought it would be worth sharing very quickly. And what we've got here is some experiments that were done in a cinema. And the reason for this is I've already said that with things like breath emissions, very dependent on the individual, will vary from person to person. So what this experiment was really good for, I think, is that they looked at 300 people in a cinema viewing, or 250, and then they could get a kind of average idea of the emission rates per person, which hadn't really been done before. So they basically sampled in the outlet from this cinema screen, lots of fancy instrumentation to measure lots of different compounds. And what this is showing is 4 different viewings of the same film. So these were on subsequent days. You can see the dates here. What we're looking at is CO2 on the left-hand axis here in black, and acetone and isoprene on the right-hand axis in these different colors. And you can see these are all breath emissions, and they all follow more or less the same pattern as each other. So they tend to go up and down together, as you'd expect. Now, what the really interesting thing is about these is that when the scientists looked at these traces from different films with different audiences on different days, the same film, different audiences, different days, they noticed that these traces were absolutely identical. So all the peaks were happening in the same place. And what they found for these 2 red lines is that there's a particularly suspenseful part of the film. So this is the Hunger Games. And for those of you who've seen it, Katniss is facing some grave danger, and the whole audience is holding its breath. So you can see everyone going, and then after the danger has passed, they all breathe out. And you can see that at the same point in every film. So really interesting, and lots of potential uses of this sort of analysis. So what the same group of scientists also found was that when people were watching a film that was scary, like horror, they would give out different ratios of these different breath emissions to if they were watching a romance or a comedy. And this then starts to give you applications around, I mean, the military, you can imagine, are interested, because if you can sniff out fear on the war field, there could obviously be potential applications of that. So some really interesting psychology going on here, that there's some sort of link between mood and the emissions you give off. Okay, so I think this is the last thing I was going to show you now before I sum up. And this is basically the same group. And what we're looking at this time is some measurements that were taken in a football stadium. And it's not strictly indoors, but it's kind of under the eaves. So it's kind of half and half. But what we're looking at is the traces of some products from a football game. So the grey is CO2. And then we've got 3 different tracers. So what we're looking at, first of all, is ethanol, shown in gold. And what this shows is some quite interesting stuff. So you've got the 2 halves of the game. So we've got half time in the middle. And what this is showing is that as people come into the stadium, you start to pick up the CO2 as they're all breathing, but you also start to pick up ethanol because they've all come in with a pint of beer at the start of the game. And then the beer gradually gets drunk during the first half. They all go out in the second half, go and get another pint and come back, and you can see the ethanol and the CO2 going back up again. This one is showing skin oxidation products, and again you can see a really nice correlation between when people are coming into the stadium and you're getting the CO2, and then a bit of a dip here at the end of the first half and then going back up again. And the one that looks a bit different is smoking, and the reason for that is that smoking was banned in the stadium So they had to go out somewhere at half time and have a cigarette, and then they'd come back in after half time and they'd still be off gassing some of the smoking products, so acetonitrile in this instance. Right, so what about solutions? So one thing that's been touted a lot recently, particularly with COVID, is maybe we can use indoor air cleaning devices. So I'm not talking about the extreme hospital cleaners like I was talking about earlier. This is just the ones that you can get on Google, and there are hundreds of these things, different shapes, sizes, different prices. Now, we found from a study we did in 2017 that these aren't a good idea generally. And again, you can see the reason for that is that this is what happened when we turn one of these things on in a PC classroom at the University of Leeds. We got very high concentrations of the hydroxyl radical again, leading to other products. There wasn't even evidence that they removed the viruses that they were meant to remove. And in fact, there's a really good report that came out by SAGE, the environmental modelling group, in November that looked at these in a lot more detail. And the take-home message for these is that the filtration ones are probably okay, but anything that works using chemicals is not a good idea to put in your home. The other thing I get asked a lot is, what about houseplants? Because this would be such a cool thing if you could just put a few houseplants in your home and remove all of these indoor air pollutants we've been talking about. Now, the problem is for houseplants to do anything in your home, you probably have to have a home that looked like this. So you would need so many, you probably wouldn't be able to move within that space. So it would be a lovely solution, but there's just no evidence that these can remove pollutants on a large scale, unfortunately. So what can we do? There are lots of things we can do, actually. We can think really carefully about pollutant sources that we bring into our homes. So particularly things containing fragrance products. Think about whether you really need a bathroom cleaner that smells of a forest on a summer's day, or whether you can just make do with something without the added scents. You can use cream cleaners and not sprays. So there's quite a lot of evidence in the literature that cream cleaners are better for your health. So sprays tend to turn the product into aerosol, which makes it easier to breathe. So the cream cleaners are better. Use a cooker hood. Something like 79% of people don't use their cooker hoods. Open the windows. Now there are caveats, and there's been a lot of work, a lot of attention as well around schools on busy roads. And then management strategies are more complicated. Generally, most homes can open a window away from the road. But I think the main message is just to think very carefully now that, when you're aware of some of the sources of indoor air pollution, just think about them and try and minimize your exposure where possible. So other issues just to leave you with really is just thinking about the changing picture of air pollution in the UK. So we're expecting over the next 10 years outdoor concentrations to get really even lower of some pollutants. Interestingly enough, we're expecting ozone concentrations to go up outdoors, which will have implications for indoors because much of the chemistry for indoors is initiated by ozone. There's issues around our indoor versus outdoor exposure and indoor versus outdoor toxicity. So for instance, I showed you very high concentrations of particles we can be exposed to indoors when we cook. At the moment, nobody has any idea if those particles are more or less toxic than what we breathe in outdoors. Changing patterns of behaviour. So after COVID, it's likely more of us will switch to working from home. So, the air quality within our homes is going to become even more important. And indoor exposure overall to air pollution will become an even bigger part of the pie. So at the moment, we already have a lot of our exposure indoors, but that's going to become even more important in the future. Okay, so just leave you with this and go to questions, but this is an interesting advert. So basically, this serum is being pushed to protect you from pollution. So I thought it was quite interesting that in order to save yourself from the effects of air pollution, you put something on your face that can then pollute the air. Interesting dichotomy there. Okay, thanks everyone for your attention, and like I say, happy to take questions.
Thank you, Nick. That was a really interesting talk with lots to think about, and we've had a very engaged audience with already lots of questions in the chat. Yeah, so what I'll do is I'll just start reading them because I don't think the recording gets to actually see the chat, and then we'll go through them. So the first question is from Helen McIntyre. He's asking how much variation is due to the cooking method versus the food in question from the beginning of your talk. So can this be used to promote healthier cooking methods in general? For example, steaming healthier than frying, for example?
Yeah, that's a really good question, actually. So I didn't talk about that. So if you cook on a gas stove, you will have higher particulate matter than if you cook on an induction hob. So some of that will be coming from the flame on the gas stove. Some of it will be coming from the meat. So there's definitely evidence that cooking vegetarian food gives you lower emissions, and steaming would give you lower emissions. Probably no emissions actually steaming. It's really the frying. So absolutely. And like I say, it's easy for me to say that as a vegetarian. It's not really an issue for me. But I think this all ties into messages around climate change as well, where it's better for everyone if we all eat less meat. So I think there's lots of health positives if we all fry less meat. The other thing I think is around messaging around new homes. There's been some talk by government about not putting gas into new homes. So that gets rid of the problem with gas stoves, but there's no real alternative to radiators at the moment for the heating system. So it's really tricky. But I think another example of where policy could be a bit better joined up between some different things.
Excellent. Sounds like that's a ongoing research topic then.
Yeah, absolutely.
Our next question from Juan Levy is asking about the Thanksgiving study and wondering, was there a ventilation system running during that study?
Oh, I can check and get back to you. If there was a mechanical ventilation system in the test house, certainly. It may have been switched off for that day, but I can, if you email me afterwards, I can send a paper and let you know. I think it was about, I'm trying to guess, because there was some recirculation. So I think fresh air that came in when it was working was maybe 0.5 per hour of fresh air. But I can look that up.
Okay. I had a question. When you were talking about the air fresheners, you talked about how the ozone is an important factor in the indoor, and I'm very familiar with that being important in outdoor. Can you talk about how the ozone reacts, especially with the emissions of the air fresheners, to create more particulate, you said?
Yeah, so basically ozone can come in from outdoors through windows and doors. So that's how you can get it in the home. So it will vary on time of day, time of year, where you live, for instance. It's typically around between 20 and 70% of outdoor concentration, depending on furnishings indoors. So it's very sticky. So if you have lots of fleecy furnishings, carpets, you'll probably have a lower concentration indoors. And if you're somewhere like a laboratory, for instance, it's generally, like lino and hard surfaces. And then, ozone, just like it would in a forest environment where you have lots of biogenic emissions, you see the blue haze in forests, that comes from the same sort of reaction. So hydroxyl and ozone can react with fragrance compounds to give you particulate matter. So it's quite well known that this happens outdoors, but less well known that it happens indoors. So it's the same reaction or reaction.
Oh, very interesting. Well, that's something I learned today then.
Good.
The next question is again from Helen McIntyre. So saying hospital ward cleaning, not used to seeing some of these in parts per million. Was there any impact of this cleaning methods on the materials or fabrics in the wards?
So I don't know if anybody's done those studies. Certainly at those concentrations, you would expect things like rubber to degrade, for instance. I mean, we don't do that in the UK, I'm glad to say. So this seems to be a North America thing. So I don't know is the answer to that question, but I would imagine if it's repeatedly in some of those wards, you would see damage. But this is how smog was first discovered in Los Angeles in the 50s, because fires started cracking from the high ozone concentration. So you would expect to see damage, I think.
Oh, right. Now Jim has quite a long question. Jim, would you just like to share your microphone and ask your question yourself, or?
Yes, can do if you can hear me. Let me just open the chat because I forgot my own question now. So I'll just go back to the very start of your presentation when you made the comment about smoking status and the pronounced effect it has on indoor air quality. And I wondered, do we start with that as when we're thinking about ventilation advice? Does that sort of lead everything else in terms of how we address other indoor sources or activities? And if not, it really seems a challenge about how do we decide what's most significant for health and how to balance all these different exposures? And are there other combinations of sources and buildings and behavior that are just as important that we need to kind of have on par with smoking status when we're thinking about what advice we give to people at home?
Yeah, that's a really, that's the question that probably needs a much longer answer than I've got time to give it. But I think the short answer is probably yes. And I guess the real thing that I think we need to address is things like social housing, where the resident has no control on the conditions. So you can imagine maybe there's damp, maybe they can't open the windows because they're next to a busy road, maybe the windows won't open. So I guess some of these conditions for people in more deprived areas are probably pretty grim. And I imagine that feeling where they can't do anything about it is pretty depressing. So I think there will be sources, and maybe one of the best things you can do, and this will be news to this group, is to really think about ventilation. And again, some of the really low quality social housing probably hasn't got very good ventilation. So maybe some around ventilation standards would be really good, I think. And particularly ways of making sure that landlords are responsible for, making sure that the ventilation is adequate. I'm not sure how much that is enforced at the moment.
Thank you. We have a couple more questions. One from Bernard Hornung asking about the use of aericides. And maybe in the same question, I'm also going to ask Patrick Fox is asking about the impact of your choice of paints on indoor air quality. Could you comment on those two?
I've never heard of aericide. I'm not quite sure what that is. I don't know if the person who put that question in can just maybe tell me exactly what it is or what's in it.
Thank you very much indeed. Can you hear me?
Yes.
Okay, well, I'll just introduce myself. I'm Bernard Hornung, and I'm a consultant with Coltraco Ultrasonics. An aericide is a brand name. It's a NASA invention, and it's an air purification system.
Okay, do you know how it works? It would be very hard to
I can send you the details. It would be too long for this seminar.
Okay.
It's very, very complicated, but it appears to work well, and it does appear to address most of your concerns. So I'll send it through to Dr. Helen, and I'd be most grateful if you were able to comment on it.
Okay.
Thank you so much.
If there's information about how it works, I should be able to do that, but yeah, okay.
Most kind of you. Thank you.
And I think the other question, paints, yes. So you can definitely buy paints now that are labelled as low VOC. So I think paints is one area where things have improved a bit over the last 10 years or so. So they're definitely much better than they were. And I think the guidance is the same as well. We know that emissions are higher from, freshly painted walls, for instance. So just make sure you ventilate when you first paint, pick low emission paint.
We also have a question asking about NO2, specifically in relation to cooking and traffic.
Okay, that's quite an open question. I just wonder if someone can say a bit more what they're thinking there.
Yes, I don't know if you can hear me. Very much interested in, obviously, the pollutants of principal public concern, which are fine particulates, PM1, but also NO2, given the problems with the young school girl who died. That's outdoor source, but I understand also indoor sourced problems can arise with NO2 as well. And I just wondered if they were being included in the overall assessments for indoor air quality. In other words, outdoor air coming into the building with ventilation and being considered as part of the overall risk to people's health.
Yep, I mean, we certainly consider NO2 in our model. One of the biggest problems, I think, it goes back to what I was saying about the difference between indoor and outdoor toxicity. So you can do various things outdoors as well, actually, that will reduce NO2 and increase ozone concentrations because of reactivity between them. And one of the things we don't know, we know that if ozone and NO2 are harmful pollutants, but I don't think anybody knows, I could be wrong, if we increase NO2 by a microgram per meter cubed and we decrease ozone by a microgram per meter cubed, is that better or worse than the other way around? And I think what we still need to understand is more about the differential health impacts of pollutants, because quite often we will do something that will reduce one pollutant. So like reducing outdoors increases ozone outdoors, same indoors, you've got this kind of, you know, negative relationship between them. But at the moment, we don't know enough about the differential impacts, I think, of different mixtures, whether it's indoors or outdoors. So I think that's a big issue with trying to decide what the impacts of pollutants are.
I guess we can only be governed by people like the World Health Organization, can we, in terms of, you know, what exposure levels should be?
Yeah, but even then, I think it's quite, because when you look at ozone, you tend to have a different guideline for ozone. So you talk about 8-hour rolling averages, and you know, I think it's really confusing for most people to understand how you would, you know, what you'd want to know is if NO2 goes up 5 ppb, but ozone goes down 5 ppb, is that better or worse for health if you're exposed to that air mixture? And I don't think anyone can really answer the question. So I think it's quite difficult at the moment to fully understand the health impacts, and PM, people understand even less about PM and the differential toxicity of different compositions of particulate matter. But it's really important that we understand that.
Hopefully the new guidance from the World Health Organization will give more clarity when it comes out, I think in the end of June.
Yeah, hopefully.
Thank you very much.
Well, I think with that, that's a good place to end. Unfortunately, I don't have time to read the rest of the comments, but there was a good discussion going on in the chat. And I'd like to take this opportunity just to thank you again, Nick, for giving a talk and yeah, talking to us about this topic. And hopefully we'll have more seminar series coming that will be of interest to everybody, and to keep your eyes open and posted for our next announcements about that. Thank you, Nick.
Thank you.